Okay, so this discussion will be about geometric progression. So just a quick recap. We discussed so far the arithmetic progression, the harmonic progression, and today we're going to discuss the geometric progression. Okay, so first things first here, we have to first clearly define and then understand what we mean by geometric progression. So the definition of a geometric progression is that it is a series of numbers having common ratio. So they have common ratio. So this is different from arithmetic progression, since for arithmetic progression, we usually look for the common difference, which is symbolized by letter D. For geometric progression, we are after about what is the ratio, symbolized by a letter R. This is not radius but ratio. So first, let us have this example and understand a geometric progression. So this is an example of a geometric progression, and let us analyze what what made this series a geometric progression. So if we divide 6 by 2, the ratio, we get 3. Similar to 18 divided by 6, we get as well 3. And then 54 divided by 18, we get 3. So the common ratio here is actually 3. Okay, so we write here that our R for this geometric progression has a common ratio of positive 3. Okay, so that's what we mean by a geometric progression. So it means that the common ratio is actually 3. Okay, so clearly, if we extend this example, you can see that 6 is actually equal to 2 times 3. Similar to this one, 18 can be found using by the product of 6 times 3, while for this one, 54 is the product of 18 and 3. Okay, now let us assume, okay, for this problem, let us going to say that let 3 be equals to R, while A be while 2 while 2 is equals to the first term, this one. So this is our first term. Going to say that this one is actually just simply equals to A. So in short, we could see that this one is A times R. For this second term, now this is for the second term, 6. For the third term, we see that 6 is can be found this one. We have to substitute the value of 6 here to here, which will be equals to AR, and then instead of 3 we're going to substitute it with R, so we get AR squared. For this one, we get the value of 18. 18 is equals to this, so we just have to substitute that one here, so we get AR squared, and then substitute R to 3, so we get AR cubed. Now notice that there is a pattern to how we get the next term. So in short, clearly you would see that um, 2, that's the first term, the second term, the third term, and then the fourth term. Let's just focus there. You, you would typically see that the first term, r, can be found simply by using this a, r, ar, ar 1 minus 1, because this would leads to a r to the power of 0 is just a. For the next one, which we get using that one, this is actually equals to a r to the power of 1, and this one is a r to the power of 2, this, and this one is a r to the power of 3. Now the pattern here is on the exponent of the ratio. So we could make a standard form of knowing what should be or what could be the next term using this equation. So the nth term is can be found using this equation, the first term times the ratio to the power of n minus 1. So this is the general equation for determining what is the nth term in a geometric progression. Now, just like in arithmetic progression, we are also after of the sum of all the terms. No? So in geometric progression, we're going to find out what will be the sum of the terms, the sum of the terms. So let's look for an equation that would do this, do the work of getting the sum of all the terms. So let us proceed. So let's start here in our example earlier, this one. So let's find out what is the sum of all these, of all the terms there. So for the first term, that is just simply actually equals to a. So let's make this is the sum. A is equals to, since 1 minus 1 is just 0, and any exponent raised to the power of 0 is just 1. So 1 times a is just a. Let me just change this one to r, so to avoid confusion. Okay, so r to the power of 0 is just simply 1. 1 times a is just a. So that's our first term. For the second term, well, that is just actually equals to a times r. For the third term, that should be a r squared. And for the fourth term, that's going to be a r cubed. Now, if we have plenty or several of these terms, then we could say that this should be how we get the total sum. Okay. Now, what I'm going to do here is I'm going to multiply this equation, okay, this equation by r. Okay. So I'm gonna multiply this by r. So this is going to be r times s, and on the right side is going to be um, a times r plus a r squared plus a r cubed plus a r4 plus a r. Okay, so um a r, this one, hmm, this one, let me highlight this. So a r n minus 1 times r, so we get a r, the sum of the exponent, and that should give us a r to the power of n. So this becomes r to the power of n. So this will be our second equation. Okay, so let's say this is our equation 1 and this is our equation 2. Now what I'm going to do now is actually um, multiply equation 2 by negative 1. So this becomes negative rs. For the right side, this becomes negative ar. Oh, my bad. So this becomes negative ar squared, negative ar cubed, negative ar4, and this one, oops, that should be negative, negative ar n. So this becomes our equation 3. Now, if I were going to add equation 1 and equation 3, so next step here is I'll going to add, because this is a trick to get the equation of the sum of the terms in an arithmetic in geometric progression. So I'm gonna add s and then rs equals that these terms, I want to highlight this one, these terms from here up until here, okay, is similar to this until that part or in between, because note that this is positive, that's negative. Okay, so this means that this part will simply vanish or cancels out to this part. Okay, so the remaining terms here, this one, this will be left because there's no terms here that would cancel that term, and this term here on the equation 3, because there's no term on equation 1 that would cancel this term. So we get what's left here is a minus a r to the power of n. Let's continue, and then we simply simplify this, so we get s1 minus r on the left side. On the right side, we simplify, we factor out the a, so we get 1 minus rn. After that, we divide both sides by 1 over r, 1 over r. So what's left here is the sum of all the terms in geometric progression is actually equals to a, the first term, multiplied by 1 minus r to the power of n, okay, divide by 1. And this is actually the equation in solving the sum of the terms in geometric progression. So that's how we derive that one. So this is a very clever way. This is a trick, a mathematical trick to solve for the sum. And I think um, this is very important, particularly if you are actually studying in physics, because this would somehow surface. Okay. So at this moment, I think it would be wise for us to have a sample problem. So let's proceed and apply what we learned so far. Okay, so let's proceed here with a sample problem. So for this problem, we have here 8 terms. So this is the first, second, third, and so on and so forth. And this is a geometric progression. Okay. Now, the problem here states that the ratio of the earth and third term is 243. So meaning, we could say that the eighth term divided by the third term is actually equals to 243. Now, what is asked here is we have to look for the value of the ratio or r. So we have to find what is the value of our r. Okay. Now, to do this one, for the third term, we get the value of the third term of a geometric progression using this equation, the first term times the ratio and then n minus 1. So for the third term, this should be a r 3 minus 1, which gives us a r squared. Now for the eighth term, this should be a r n minus 1. So just a r for n here becomes 8 minus 1. So this gives us a r 7. So going back to this constraint or condition given in the problem, so we could say that a8 is a r to the power of 7, a3 divided by a3, which is a r to the power of 2, that should be equals to 243. Let's proceed. So we could actually omit a here. So what's left here is just r to the power of 7 and r to the power of 2 equals 243. So this gives us r 7 minus 2 equals 243. So the ratio here is 243. We get the uh, fifth root of this one, or the square root, the power of 1/5. So this becomes 1 over 5 to the power of 1 over 5. So this, so that it would cancel out. So what's left on the left side is r, while on the right side, 243 to the power of 1/5 is actually equals to 3. So the ratio is actually 3. And that is the answer. Okay, so this is our second problem. So we have to find the 10th term of the geometric progression. So this is our geometric progression. And we want to know what will be the 10th term of this series. But first, let us assess what will be the ratio of this geometric progression. So 10 divided by 5 is actually 2. 20 divided by 10 is actually 2. 40 divided by 20 is actually 2. So therefore, our ratio here is actually 2. Okay, so we already determined that the ratio of this geometric progression is equals to 2. Now, to find the 10th term of this geometric progression, we're going to use the standard equation. A, the 10th term is equals to A, the first term, times the ratio to n minus 1. So for the 10th term, the first term is 5, substitute that 1. The ratio is 2. Okay, now n here is 10 minus 1. Okay, so we have here 5. 10 minus 1 is just 9. And that gives us a value of 2560. Okay, so this is our last example. The problem here is that we want to know what is the sum of the terms until the ninth terms. So this is our geometric progression. This is the first term, second, and third. So first things first here is we're going to identify what is the ratio. So to do that one, we have to divide 57.6 by 72, and this gives us 0.8. So the ratio here is actually 0.8. Now to get the sum, we're going to use the standard equation of the geometric progression in calculating for the sum. That should be S is the first term, 1 minus r to the power of n over 1 minus r. So the first term here is 72. 1 minus the ratio here is 0.8. We have to raise this one by since this is 9, we get put here 9, so this becomes 9 to the power of 9. Okay, I think would be 9 divide by 1 minus 0.8. Okay, so let's proceed. We will plug this one in our calculator, and we get the sum of the 9 terms is actually equals to 311.7, and that's how we get the sum of the terms. I want to highlight here about infinite numbers of terms. Our sum of the terms becomes a over 1 minus r, and this is used if the ratio is less than 1. So if we have an infinite number of terms here, so our n here is infinite, the number of terms is infinite. Okay, so if that is the case and r is less than 1, so we're going to use this equation. Well, actually that is logical, because from our earlier standard equation in solving for the sum, that's gonna be 1 minus r to the power of n over 1 minus r. If n here absolutely approaches infinity, okay, or it is infinite, so this part here would simply, so it somehow it will just simply disappears. Now, if what if our r here is greater than 1 and n is also approaching to infinity? Our equation for solving the sum will be equal to oops will be equals to a r minus 1. And it is all about geometric progression.